Hello everyone, I am Dr. Rajeshwari Moganty, Professor from the Department of Biochemistry, All India Institute of Medical Sciences, New Delhi. Now this course is on PG Pathshala Biophysics. Paper is 3 on thermodynamics of living systems and bioenergetics. And this module is about the first law of thermodynamics. Now before we do the first law of thermodynamics and its importance, I would like to tell you that the thermodynamics is a study of pattern of energy change, where thermo means energy and dynamics means patterns of change. Therefore, it mainly deals with the changes in the energy and the stability of the molecules and the directionality of the change. So, basically the first law of thermodynamics is the application of the conservation of energy principle to heat and thermodynamic processes. In the universe, we know that energy exists in various forms of energy, like as internal energy, kinetic energy, potential energy, mechanical energy, heat energy, chemical energy, electrical energy, so many forms of energy. So basically these forms of energy have the ability to bring about the change or to do the work. For example, you take a ball resting on the window or any table. Then it is at a certain height. If the ball rests on the edge and then the potential energy, the ball is having the potential energy. But if you just give a push and then when the ball drops, then the ball is coming down with the kinetic energy. What does it mean? That means the potential energy which was earlier static now is converted into kinetic energy while it is coming down. Therefore, this conversion of the energy can take place. For example, conversion of the chemical energy, electrical energy to one type of energy to another. So basically the first law of thermodynamics says that only that in thermodynamics that systems cannot be, new energy cannot be created or destroyed, but it can only change from one form to another. So when you talk about energy, E, total energy of a system, that can be internal energy E, kinetic energy E, potential energy, then mechanical energy, electrical energy, and all those things together it becomes a total energy. Therefore, the system and the surrounding in a thermodynamic analysis, the system is in the subject of the investigation, and there is a boundary, that is closed surface surrounding a system through which energy and mass can enter or leave the system. So everything external to the system can be transferred into the surroundings. So what does that mean? That you have these two sorts of systems, which is called can be closed system if it doesn't exchange the energy, and other one is an open system where you can exchange energy to the surroundings. So that is what has been shown to you in the picture, and that first one is in the form of heat and radiation, and in the other it is the movement of the molecules across the boundary between the system and its surroundings. So this is also been shown to you. So with that of a little bit of introduction, now I would like to lay out the objectives of this topic, that is the first law of thermodynamics. So with that introduction, the objectives laid in this module are: what is it, the first law of thermodynamics, and what is its importance. The second learning objective is that you should be able to define the first law, that is, the total energy is conserved for any thermodynamic system and energy cannot be created or destroyed. It can only be changed from one form to another. This is the first law. When you say define, it means that you also should be able to explain. Now the third objective is to know the terminology and define heat, work, thermal efficiency, and the difference between various forms of energy. Now the fourth objective is to understand the directionality, or also can call as tendency of physical and chemical changes. The next one is to know how to estimate the potential for thermomechanical energy conversion, and lastly you should be able to explain the pressure volume curve or the PV curve. So of course I have introduced you to the surroundings and the closed and open system, but the two type of exchanges can also occur between the system. That is, one is the energy exchange, that is a heat or radiation, or the matter exchange, movement of molecules across the boundary. So that is of course there, that the movement of the matter from one system to another system. Based on this type of exchanges, three types of systems we can actually define. Open and closed systems we already know, but there is also called an isolated system. That means no exchange of matter or energy can also be possible, although isolated system is not common, but it can be there, it can exist. The total energy of a system before the process has taken place is called the initial state. Now, while the total energy of a system after the process has occurred, whether it could be a chemical reaction, whether it could be a mixing or any kind of equilibrium that is reached, then it is called the final state. Now, so you have to remember initial state, final state and equilibrium state. The equilibrium state is that condition in which no change, no further change is occurring within the system or between the system and its surroundings. So, these are the three states of the energy, that is the initial, final and equilibrium. Thermodynamic processes therefore also can be two types. One is a reversible and the other one is irreversible. Reversible happens slowly enough to be reversed, but irreversible cannot be reversed. Now, for example, I will tell you, reversible process is a process when you can add the, if you take an exchange between the two membrane and then if you remove the salt can also be passed from one side to another depending on the concentration gradient. But a reversible process is, for example, a boiling an egg. That is an irreversible process, because once a boiled egg is there, it cannot go to the original state. So, a system can be reversible or irreversible. Therefore, the first law we can say that energy can be exchanged between the system and surroundings, but the total energy of the system plus surroundings, that is the total energy, is a constant, and therefore energy of the universe remains a constant. Therefore, what actually we are trying to say in another terms or in a simplest term, the first law thermodynamics says energy is conserved, to put it in a very, very simple words. Now, heat and work, these are the two terms we learnt. Heat and work changes. How does it happen? The energy of a system will change if the heat is transferred to or from the system, or work is done by the system. So, these are the two terms. So, if the work is done by the system also, so heat and work are changing, that there are always changes in the system. So, you can say that, as I shown you in the picture in this slide, that the first law what we stated, if some amount of Q heat is represented by Q and work by W, that is added into the system, it must do either do the work. Therefore, if you say the system and the boundary and surroundings, energy is flowing, but there is no mass flow. So, heat is shown, work is done. Heat enters the system and therefore is done. So, it is actually a very simple example of any engine working or any kind of a work that is done by a system. In a biological system, now because we are concentrating on the biophysics, although the fundamental principles of the thermodynamics remain, but we are more interested in understanding the biological systems, what's happening in their energy. We will give the example. In the capacity to do the work is represented by W, and H stands for the enthalpy or the heat content. Then the first law we can write as delta H, that is change in the heat content, or we call enthalpy, is equal to Q, that is the heat, minus W, that is the work done. The change in internal energy of a system is equal to the heat added to the system minus the work done by the system. So, this is actually delta H is a change in the internal energy of the system equal to the heat added to the system, that is Q, and minus the work done by the system, Q minus W. It's a very simple equation, nevertheless it's very important. Now here we are just showing the same. If a man is using energy, taking energy by eating food or taking glucose in any metabolic processes, he uses 5 units and his energy is stored, but he is only working out with only 4 units. Actually, that means 1 energy is been stored. So the conservation of energy is actually the principle that is in the human body. The energy is used, energy enters, and then some energy is stored and some energy is being used by any physical exercise or any mental activity. So the total energy will remain same. Here you have to understand the working principle, that is the first law of thermodynamics: heat, work, internal energy, and Joule's experiment, one of the most important classical experiments which is done using the first law of thermodynamics. Here you have shown the working principle. Schematic diagram of the Joule experiment. Actually, insulating the walls are necessary to prevent heat transfer from the enclosed water to the surroundings. Otherwise, the heat loss will be there to the surroundings. Therefore, as the weights fall at constant speed, they turn the paddle wheel, which does work on water. So if this is an example, and if the friction in the mechanism is negligible, we are assuming that there is no frictional force or the energy, but nevertheless there will be some. The work done by the paddle wheel on the water equals a change in the potential energy of the weights. So this is a conversion of the energy. For example, we are assuming there is no frictional force. Therefore, 1 calorie you can convert it equal to 4.184 joules. This is important unit. Either energy can be expressed in the terms of calories or in joules. Joules is a more thermodynamic this thing, yeah, but one uses sometimes any scale depending on the scale you are the system that is you are using. Work is done on water, the energy is transferred to water, and the energy transferred appears as an increase in temperature. Now we can replace the insulating walls by conducting walls. That means energy is not let it go out in the previous case, but here we are actually using a conducting the walls, which takes the heat from the system. Therefore, we can transfer the heat through the walls of the system to produce the same increase in temperature. So either you transfer the heat or let it keep it in the internal energy. The increase in temperature of the system is a consequence of an increase in the internal energy, and the internal energy is a system function of the system. The sum of the heat transferred into the system and the work done on the system equals the change in the internal energy of the system. Therefore, total delta E is internal energy, then equal to Q internal plus work done on the system. Another method, we are giving an example of doing the work. So this is actually, previous one is a mechanical one, and here it is more of an electrical change. So electrical work is done on the system by a generator, which is driven by the falling weight. For example, if you do this, you can generate the electrical energy from a generator by driving this from using the weights. Again, this is another application, but a particular cause you are actually using. This is a piston, and here it is, what I am going to show you is the state of the gas will be described by the ideal gas law, that is PV equal to nRT, where P is the pressure, V is the volume, N is the number of molecules, R is the gas constant, T is the temperature expressed in Kelvin. And what is the value of the internal energy for the gas in this particular cylinder? Now if you look at it, first law, delta E equal to internal energy, we just talked about in the previous slide, Q internal energy plus W work done. Now this also can be written as dE, that is small d, E internal energy equal to delta into Q internal energy plus delta into work done. Therefore, that can be written as quasi-static processes. This is a type of process actually where the gas moves through the series of equilibrium states. So each one can be added up, number of them. Then we can apply the gas law, that is ideal gas law. But in practice actually what happens is, if we move the piston slowly, it will be possible to approximate quasi-static process fairly well. Therefore, now finally, how does the confined gas exchange the energy, heat and work with the surroundings? Now also you can ask, how can we calculate? How can we calculate the energy, heat or work transferred or work added or subtracted to the system? So you should be able to calculate the energy. Here we are trying to understand fluxes of the energy and the mass on the earth of the surface. Is there any balance? So if you see the picture that in an environment, the tree and environment is there. Now you can see that Rn is the net gain of heat energy from radiation coming from sun. Then lambda Et is the latent heat, that is the energy associated to the flux of water vapor leaving from the system, and H is the sensible heat. G is the heat energy by conduction to the soil. Then pH is a net photosynthesis. Delta E internal is a change in the internal energy. D is the advection. So if you can see all types of energies, then you can apply that balance of the energy. How can you apply that? There is an energy balance. Rn equal to Rns plus Rnl, and also that net flux of the mass is because of the water vapor and carbon dioxide in the environment, and therefore we can write as energy balance equation Rn minus H minus delta Et, that is the net gain of the heat energy from radiation minus sensible heat minus latent heat minus heat energy because of the conduction, and also the advection, then net photosynthesis, then you get the total energy. Sorry, not the total energy, the change in the internal energy of the system. So the system is actually can be the change in the internal system can be coming from various parameters in this particular case. So this is an example to make you appreciate that energy balance and calculation of the internal energy of any system. Again, one more application, that is a gas is confined in a cylinder with a movable piston. Here delta E internal equal to Cv into dt, that is C is the constant volume, and delta T equal to N into Cv into dt. The internal energy of the ideal gas, it only depends on the temperature of the gas and not on the volume nor its pressure. Therefore, what is the value of the internal energy for the gas cylinder? If heat is added at a constant volume, no work is done. Therefore, the heat added equals to the increase in the thermal energy. So, for example, if you see gas and they are connected, and then other side there is a two are connected, one side is a gas and one is a vacuum, there will be free expansion. Therefore, for a gas at low density, for example an ideal gas, a free expansion does not change the temperature of the gas. So, it is only the expansion, that is a physical expansion of the, will not change the internal energy. This has to be remembered. Therefore, internal energy is a state function, that it is not dependent on the process, it only depends on the initial and final state of the temperature, but not on it is not on the it is a state function not dependent on the process, how it happens. The process or the way it happens is not important. And here it is applied in the gas confined in a cylinder with a movable piston. It is an extrapolation of the previous experiment. If heat is added at constant pressure, then the heat energy is transferred, will be used to expand the substance and to increase the internal energy. Therefore, here Cp minus Cv will be equal to N into R. So, in this case, initial case, if heat is added at constant volume, there will be no work done, and if heat is added at constant pressure, the heat energy is transferred, will be used to expand the substance and to increase the internal energy. Therefore, what I am trying to conclude is that expansion is usually negligible for solids and liquids. So, for them Cp is approximately equivalent to Cv. Now, here we are using the example of a gas confined to a cylinder with movable piston. but here I am going to show the equations at a constant volume, concluding that at a constant volume, then you have typical processes will be the T different process. At constant volume, QV equal to CV into delta T, and at constant pressure you have QP equal to Cp into delta T. Now at constant, that is in case of a ideal gas, there will be Cp minus Cv equal to Nr, which is called the relationship of Mayo. Therefore Cv will be 3 by 2 into Nr, or Cv equal to 5 by 2 into Nr, in depending on the case. Therefore this example is to show the heat transfer to a system, and this is we actually summarizing the previous two slides. For solids and liquids, as expansion at constant pressure is usually negligible, then we call it as Cp equal to or approximately equal to Cv. An adiabatic process, what is an adiabatic process? Process in which no heat flow occurs into or out of the system is called an adiabatic process. Such a process can occur when the system is extremely well insulated or when the process happens very quickly. Here again we are trying to see that if work is done on the system, that is W on, is the energy transferred as a work of the system. Therefore work done on the gas is an expansion, and when this energy is added to the system, its value will be positive. So this is a PV diagram. Constant pressure W on gas will be integral of V1 to V2 PdV equal to P into V1 minus V2. If 5 liter of an ideal gas at a pressure of 2 atmosphere is cooled so that it contracts at constant pressure until its volume is 3 liters, now you can tell me what will be the work done on the gas. Now this will come out to be, if you use this equation P1 V1 equal to P2 V2, then it will come to 405. You can calculate and come to the the value, that 405 joules. The first law of diagram thermodynamics, you have to remember, this is very important. PV diagrams, this is put it in all in one. That first one is the connecting an initial state and the final state using 3 paths. In the first one we have the path A, P1, it is actually the constant pressure. The second one is the constant volume, and third one is the constant temperature. So in the first one we call it as a adiabatic constant volume. Third one is the isothermal state, which is the temperature is constant. Look at the pressure volume relationship, that in case there is the internal energy with W1 gas equal to P into V1 minus V2, whereas constant volume there is PdV equal to 0, whereas in the constant temperature then it will be minus nRT into ln V2 by V1, that is the volume 2 by the volume 1. Now here the biatomic ideal gas undergoes a cycle starting at the 0.2 atmosphere at 1 liter, and then process A to B is an expansion at a constant pressure until the volume 2.5 liter, after which it is cooled at a constant volume until its pressure is 1 atmosphere. It is then compressed at constant pressure until the volume is again 1 liter, after which it is heated at constant volume until it is back to its original state. Now what you have to do is to find the work done, that is heat and change in the internal energy in each process, and also the total work done on the gas and the total heat added to it during the cycle. The first law of thermodynamic process, adiabatic process, no heat flows into or out of the system. This is what is shown here 3 times. Adiabatic path, there is no heat flows or in or out of the system. And also we can use this ideal gas to rewrite the work done on the gas in an adiabatic process in this form: P1 V1 minus P2 V2. And therefore understanding the adiabatic process, PV diagrams is one of the most important part of the first law of thermodynamics. For example, if we take a quantity of air that is compressed adiabatically and quasi-statically from an internal pressure of 1 atmosphere and a volume of 4 liters at temperature 20 degrees to half of its original volume. Now you have to find out firstly what is the final pressure, then B the final temperature, and C the work done on the gas. So you should be able to calculate using the previous, what I have done with the previous example. The human metabolism is actually the conversion of food into heat transfer, work and stored fat. So metabolism is an interesting example of the first law of thermodynamics in action. We now take another example look at these topics via the first law of thermodynamics. Considering the body as a system of interest, we can use the first law to examine heat transfer, doing work and internal energy in activities ranging from sleep to heavy exercise. Now what are some of the major characteristics of heat transfer, doing work and energy in the body? Therefore, once the body temperature is normally kept constant by heat transfer to the surroundings, this means Q is negative. And another fact is that body usually does work on the outside world. This means W is positive. In such situations, then the body loses its internal energy, and since delta U equal to Q minus W, which is negative. Therefore, the body provides us with an excellent indication that many thermodynamic processes are actually irreversible. An irreversible process can go in one direction but not the reverse one under a given set of conditions. For example, although body fat can be converted to do work and produce heat transfers, work done on the body and heat transfer into it cannot be converted to body fat. Otherwise, we could skip lunch by sunning ourselves or walking down the stairs. Another example of an irreversible thermodynamic process is photosynthesis. This process is the main intake of one form of energy, that is sunlight, by plants and its conversion to chemical potential energy. But both applications of the first law of thermodynamics are shown in these pictures. And in one great advantage of conversion of laws into such as the first law of thermodynamics is that they actually accurately actually describes the beginning and ending points of the complex process. Such metabolism and photosynthesis without regard to the complications in between, that means delta U equal to Q minus W plus food energy in the body. Delta U is actually the stored energy. So let me summarize the first law of thermodynamics, which is very simple. Delta U equal to Q minus W. Now where delta U is actually change in the internal energy of the system, Q is the net heat transfer, that is the sum of all heat transfers into and out of the system. Now W is the size of the net work done, how much work has been done, the sum of all the work done on or by the system. So both Q and W are actually energy in transit, and only delta U actually represents the independent quantity capable of being stored. The examples I have given, the body and then temperature, body storing energy, and therefore the metabolism of the living organisms, photosynthesis of plants is actually a very good example, specialized types of heat transfers, doing work and internal energy systems. So with this, I hope you understand and appreciate the importance of first law and its applications in biological systems. And now we will see the second law in the next module. Thank you.